Right now, as you're watching this video, a comet from another star system is barreling toward our inner solar system, carrying a mass so enormous that it's forcing astronomers to rewrite the textbooks on interstellar objects. What if I told you that Comet 3I, Atlas, only the third interstellar visitor humanity has ever confirmed, weighs an estimated 33 billion tons? That's not a typo. 33 billion tons of frozen material from a star system we've never seen, traveling through the void of space for potentially billions of years, now passing through our cosmic backyard. To put this into perspective, that's roughly 165 times the mass of the Great Pyramid of Giza. It's heavier than every cruise ship on Earth combined, multiplied by 10. This single frozen wanderer contains more mass than humanity has ever launched into space throughout our entire history. And here's what's truly bending scientists' minds. Based on everything we know about how objects get ejected from star systems, something this massive should be nearly impossible. The physics simply doesn't work. By the end of this video, you'll understand exactly how astronomers calculated this staggering number, why it defies our models of planetary formation, and what this cosmic heavyweight might be telling us about alien solar systems we've never observed. Stay with me here, because this discovery is about to change everything we thought we knew about what's wandering between the stars. Let me put these numbers into a context that will truly blow your mind. When astronomers confirmed the mass estimate for 3I Atlas, the reaction across major observatories was something between disbelief and excitement. Leading researchers in trans-Neptunian object studies called it one of the most significant mass measurements in solar system science this decade. Here's why that statement isn't hyperbole. The first confirmed interstellar object, Oumuamua, was estimated to weigh somewhere between 1 million and 10 million tons, a tiny speck, cosmically speaking. The second, Comet 2I, Borisov, clocked in at roughly 500 million tons. Scientists thought that was substantial. 3I, Atlas, is approximately 66 times more massive than Borisov. 66 times. Think about what this means. If Borisov was a sedan, 3I, Atlas, is a fully loaded oil supertanker. If Borisov was a house cat, 3I, Atlas, is an elephant. The scale difference is so dramatic that it forced researchers to question whether their instruments were malfunctioning. But here's where it gets truly strange. Objects this massive don't just get thrown out of star systems easily. The gravitational energy required to eject 33 billion tons of material from a planetary system is absolutely enormous. It requires either a catastrophically violent event, like a giant planet plowing through a debris field, or conditions so extreme that our current models can't explain them. And yet here it is, sailing through our solar system as if the laws of celestial mechanics simply don't apply. So the question that's keeping astronomers up at night is this: what kind of cosmic event creates a 3 billion-ton messenger, launches it into interstellar space, and sends it on a billion-year journey to our doorstep? Before we dive into the mystery of how 3I Atlas got so massive, you need to understand how astronomers weigh objects millions of kilometers away and why this particular measurement is so extraordinary. You see, we can't exactly put a comet on a scale. When an object is floating through space, we have to get creative, and the methods astronomers use are both elegant and surprisingly precise. There are 3 primary techniques for determining a comet's mass, and each one gave researchers a piece of the puzzle. The first method relies on the object's gravitational influence. If a comet is massive enough, it will ever so slightly deflect dust particles and small debris in its vicinity. By tracking the trajectories of material in the comet's coma, the fuzzy cloud of gas and dust surrounding the nucleus, astronomers can work backward to calculate how much gravitational pull is affecting that material. Think of it like measuring the weight of a magnet by watching how it moves iron filings. The second method involves analyzing the comet's outgassing behavior. When a comet approaches the Sun, its surface heats up, causing frozen volatiles, water ice, carbon dioxide, methanol to sublimate directly into gas. This outgassing creates jets that actually push against the comet, altering its trajectory in measurable ways. The amount of push depends on two things: how much gas is being released and how massive the nucleus is. A heavier comet requires more push to change course. By comparing the outgassing rate to the trajectory changes, scientists can estimate mass. The third method is the most direct, measuring the size and estimating density. If you can determine how big an object is and make reasonable assumptions about what it's made of, you can calculate mass using basic physics. For most comets, this is straightforward. They're dirty snowballs with densities between 0.3 and 0.6 grams per cubic centimeter, lighter than water. Now, here's where things get strange with 3I, Atlas. When astronomers applied these methods, they got numbers that didn't match expectations at all. The gravitational analysis suggested enormous mass. The outgassing behavior indicated a nucleus far larger than initially believed. And when the size estimates came in from infrared imaging, the picture that emerged was shocking. 3I Atlas has an estimated nucleus diameter of approximately 50 to 70 kilometers. For comparison, the most famous comet in human memory, Halley's Comet, has a nucleus about 15 kilometers long. Comet 67P, which the Rosetta mission orbited and studied extensively, is just 4 kilometers across. We're talking about an object potentially 15 times larger than anything we've sent a spacecraft to visit. But here's the detail that made researchers sit up straight. The density calculations suggested this isn't just a bigger dirty snowball. The numbers pointed to a density significantly higher than typical comets, closer to 1 to 1.2 grams per cubic centimeter. That's denser than ice. That's denser than most comets by a factor of 2 or 3. Something about 3I, Atlas, is fundamentally different from the comets we know. It's not just bigger, it's built differently. And that realization sent researchers scrambling to understand where this thing could possibly have come from. Now, what I'm about to reveal next is the detective story that led astronomers to their mass estimate and why the number 33 billion tons has such extraordinary implications for our understanding of other solar systems. If you're fascinated by cosmic mysteries like this, you're exactly who this channel is made for. Hit that subscribe button and the notification bell so you never miss when we uncover what's really happening in our universe. Because here's what's coming. I'm going to walk you through the investigation that produced this mass measurement, including the controversy between competing research teams. Then I'll reveal the 4 theories scientists have proposed to explain how an object this massive got ejected into interstellar space. And the 4th theory? It involves a type of planetary system we've only recently discovered one that might be far more common in the galaxy than anyone imagined. Let's start from the beginning. The story of how astronomers weighed 3I Atlas reads like a scientific thriller, complete with competing teams, surprising data, and a twist that nobody saw coming. It began just 2 weeks after the comet's discovery. Researchers at NASA's Jet Propulsion Laboratory were the first to notice something unusual in the trajectory data. The comet wasn't following the path that pure gravitational physics predicted. This isn't unusual for active comets. Their outgassing creates small rocket-like effects that alter their courses, but the magnitude of deviation they were seeing was extraordinary. Either 3I Atlas was outgassing at rates far higher than observations suggested, or the nucleus was far more massive than anyone had estimated. These findings were shared with colleagues at the European Space Agency's Near-Earth Object Coordination Center. Within 48 hours, 3 independent teams were analyzing the same data, and they were all reaching the same puzzling conclusion. The mass estimates from trajectory analysis were coming in 10 to 20 times higher than initial predictions based on brightness. Here's where the detective work got interesting. Thermal infrared data was obtained from high-altitude observatory instruments. These measurements allowed researchers to estimate the nucleus size independent of brightness, which can be misleading due to surface reflectivity. The result was stunning. The nucleus wasn't 20 kilometers across, as initial estimates suggested. It was at least 50 kilometers, possibly larger. This was no ordinary comet. This was one of the largest cometary nuclei ever observed. But even with a 50-kilometer nucleus, the mass numbers didn't add up. A typical cometary density would give you around 10 to 15 billion tons. The trajectory data was suggesting something significantly heavier. The puzzle gained another piece when spectral analysis focusing on the ratio of gas to dust in the coma was published. The findings were startling. The gas-to-dust ratio was inverted from what's typical for solar system comets. There was far more dust, far less gas, suggesting the nucleus wasn't ice-rich like most comets, but instead dominated by rocky or silicate materials. This was the key insight. If the nucleus was more rock than ice, its density would be much higher, and a higher density at that size meant a much higher mass. When density estimates were combined with size measurements and trajectory analysis, all 3 datasets converged on the same answer: approximately 33 billion tons, with an uncertainty range of 25 to 45 billion. The announcement came through a joint statement from major space agencies. The scientific world reacted with a mixture of amazement and skepticism. Some researchers immediately questioned the density assumptions. Others wondered if the trajectory perturbations might have other explanations, perhaps gravitational influence from an unknown outer solar system object, or unusual radiation pressure effects. But as more data came in over the following weeks, the 3 billion-ton estimate held firm. Additional observations from major observatories around the world all supported the mass calculation. And that's when the real question moved to the forefront. How in the cosmos did something this massive end up wandering between the stars? To understand why a 3 billion-ton interstellar object is so baffling, you need to understand how objects get ejected from planetary systems in the first place. Here's the basic physics. For any object to escape its home star's gravity, it needs to reach escape velocity. The farther from the star, the lower the escape velocity required. That's why most ejected comets come from the outer reaches of planetary systems, the equivalent of our Kuiper belt or Oort cloud, where escape is easier. But there's a catch. Objects in the outer solar system move slowly. To give them the kick needed to escape, you typically need a close gravitational encounter with a massive planet. This is called gravitational scattering, and it's how most comets get ejected from solar systems. Now, here's the problem with 3I Atlas. Gravitational scattering is mass-dependent. Smaller objects are easier to deflect and eject. Larger objects have more inertia and require more energy to accelerate to escape velocity. The amount of energy needed scales with the object's mass. For a 3 billion-ton object, the energy requirements are staggering. You would need an extremely close encounter with a gas giant, Jupiter-sized or larger, at very specific geometries. The probability of such an encounter happening is low, and the probability of it happening to an object this size is even lower. Experts in planetary system dynamics ran the numbers. Their conclusions indicated that ejecting a 30 billion-ton object via conventional scattering would require orbital conditions so precise that the probability is roughly 1 in 10 million for a typical planetary system. 1 in 10 million for one object. Yet here it is. So how do scientists explain it? 4 major theories have emerged. Theory 1. The giant impact remnant. This theory proposes that 3I, Atlas, isn't a pristine comet at all. It's a fragment from a massive collision between 2 planetary bodies in another star system. Think about when a Mars-sized object hit the early Earth, creating the Moon. That impact launched enormous amounts of debris into space. Most fell back to Earth or was captured by the Moon's gravity, but some material could have achieved escape velocity. If a similar collision happened in another solar system, particularly in the outer regions where escape velocities are lower, massive chunks of debris could be thrown into interstellar space. The high density of 3I, Atlas, with its rocky composition, would fit this model perfectly. Theory 2. The dying star scenario. When stars reach the end of their lives, they undergo dramatic transformations that can destabilize entire planetary systems. Red giant expansion, stellar mass loss, and eventual white dwarf formation can send previously stable orbits into chaos. In this scenario, 3I Atlas could have been a large planetesimal or dwarf planet in a stable outer orbit for billions of years. When its parent star began dying, the resulting gravitational chaos could have flung it outward with enough velocity to escape. The beauty of this theory is that it doesn't require a lucky planetary encounter. The star itself provides the energy through its death throes. Theory 3. The binary star ejection. More than half of all stars in the galaxy exist in binary or multiple star systems. These systems are dynamically complex, with gravitational interactions that can sometimes catapult objects at enormous velocities. If 3I Atlas formed around one star in a binary pair, interactions between the 2 stars could create gravitational slingshot effects far more powerful than any single planet could produce. This mechanism could more easily explain the ejection of a 3 billion-ton object. Recent spectroscopic analysis of 3I Atlas's composition has found isotope ratios suggesting formation in an environment unlike our solar neighborhood, possibly consistent with a binary system origin. Theory 4. The Super Earth Factory. This is the theory generating the most excitement among planetary scientists. Recent exoplanet surveys have revealed that the most common type of planet in the galaxy is the super-Earth rocky worlds between 2 and 10 times Earth's mass. These planets are everywhere, yet our solar system has none. Systems with super-Earths are dynamically violent during formation. These massive rocky worlds migrate, scatter smaller bodies, and create chaos. Simulations show that super-Earth systems eject far more material and larger material than systems like ours, with small inner planets and distant gas giants. If 3I Atlas came from a super-Earth-dominated system, its enormous mass becomes less surprising. Such systems might routinely produce and eject massive objects that would be extremely rare in a solar system like ours. Leading researchers have called this the most elegant explanation because it connects the mystery of 3I Atlas to broader questions about planetary system architecture. But just when scientists thought they were narrowing in on an answer, new observations revealed something that complicated everything. Here's where the story takes an unexpected turn that has researchers questioning their assumptions all over again. High-resolution imaging data revealed something shocking about 3I, Atlas's structure. The comet isn't a single solid object. It appears to be what astronomers call a contact binary, 2 or possibly 3 large masses in direct physical contact with each other, held together by gravity and possibly by cohesive forces. Think of it like a cosmic snowman, but made of mountain-sized chunks of rock and ice pressed against each other. This changes everything about the mass interpretation. You see, contact binaries are unstable over long timescales. The gravitational stresses, combined with rotational forces, tend to either merge them completely or tear them apart. For a contact binary to survive billions of years of interstellar travel, the components would need to be pressed together with significant force, or the journey wasn't as long as we assumed. Here's the first complication. If 3I Atlas is a contact binary, its formation story becomes even more puzzling. Did it form this way in its home system? Or did 2 separate objects somehow collide and stick together during the interstellar journey? The latter seems fantastically unlikely, but the former raises questions about what conditions create stable contact binaries at this scale. Experts on binary asteroids and comets calculated the rotational period needed to keep a 3 billion-ton contact binary stable. Their results revealed an apparent paradox. The current rotation rate of 3I Atlas, approximately 11 hours per rotation based on light curve analysis, should be creating enough centrifugal stress to pull the components apart. Yet the structure persists. This led to the second complication. Some researchers are now proposing that the mass estimate might need revision, not because the measurements are flawed, but because the density assumptions don't apply to a contact binary. If there are significant void spaces between the components, the average density could be lower and the mass could be reduced to perhaps 20 billion tons. But here's the twist within the twist. Even 20 billion tons is extraordinarily massive for an interstellar object. It still demands explanation. Meanwhile, a controversial alternative has emerged from researchers who point out that the contact binary structure, if artificial, would be an efficient way to transport maximum mass through interstellar space. By connecting multiple objects, you reduce the surface area to volume ratio, minimizing erosion from cosmic rays and interstellar dust. To be clear, these researchers aren't claiming artificial origin, but they argue that the contact binary structure should be investigated thoroughly, noting that nature rarely produces such convenient configurations. The mainstream scientific community remains skeptical of any artificial hypothesis, but the structural mystery is real. Why does 3I Atlas look like this? How has it survived in this configuration? And there's one more complication that emerged recently. Spectroscopic analysis of the junction region, where the components meet, shows different chemical compositions than the outer surfaces. The junction appears to be enriched in organic compounds and hydrated minerals. This could mean the components were once separate, accumulated organic material, and then came together. Or it could mean some chemical process is occurring at the contact zone that we don't understand. The 3 billion-ton question has become even more complex. We're no longer just asking where this mass came from. We're asking how it's structured, why it's structured that way, and what processes have been occurring during its inconceivably long journey. Every answer seems to generate 2 new questions. All right, I genuinely want to know what you think about this cosmic heavyweight. After everything we've covered, which explanation for 3I, Atlas's enormous mass, makes the most sense to you? Option A. Is it a fragment from a catastrophic planetary collision debris from an ancient cosmic crash in another star system? Option B. Did a dying star destabilize its planetary system, flinging this massive body into interstellar space? Option C. Could it have come from a violent binary star system where gravitational chaos ejected it at high velocity? Or option D. Is this evidence that super-Earth systems, the most common planetary architecture in the galaxy, routinely produce massive wanderers like this? Drop your vote in the comments below. I'll be reading every response and pinning the most thought-provoking theories. And if you have a background in astrophysics or planetary science, I especially want to hear your take. Some of the best insights on this channel have come from experts in the audience who noticed connections I missed. Now, let's talk about why a 3 billion-ton interstellar object matters far beyond the headlines. This discovery has implications that ripple across multiple fields of astronomy and planetary science. For researchers studying exoplanetary systems, 3I Atlas provides the first physical sample, albeit one we can only observe remotely from a planetary environment completely different from our own. The chemical composition of this object is a window into the building blocks of an alien solar system. Every spectrum we capture is data about how that distant system formed. For scientists modeling planetary system dynamics, the mere existence of something this massive forces a recalibration of ejection probability calculations. If one 3 billion-ton object has passed through our solar system during the few years we've been able to detect such things, statistical models suggest there could be millions of similar massive wanderers throughout the galaxy. The interstellar medium might be far more crowded with planetary debris than we assumed. For astrobiologists, the implications are profound. Objects of this size could potentially carry subsurface liquid water for billions of years, heated by radioactive decay. If life can survive in isolated ocean worlds beneath ice shells, as we suspect might be possible on moons like Europa or Enceladus, then massive interstellar objects could theoretically transport living organisms between star systems. I want to be clear. There's no evidence that 3I Atlas harbors life or ever did, but its existence raises questions about whether the galaxy might have natural transport mechanisms for biological material that we never considered before. For future space exploration, the discovery changes our priorities. Several research groups are now calling for dedicated interstellar object intercept mission spacecraft that could be rapidly launched to catch objects like 3I Atlas before they leave our solar system. Proposed mission concepts, currently in development by major space agencies, were designed for exactly this scenario. If another massive interstellar visitor is detected with enough warning time, we might actually be able to rendezvous with it. The scientific return from physically sampling material from another star system would be incalculable. The lesson of 3I Atlas is that the universe is constantly delivering gifts to our cosmic doorstep. We just need to develop the capability to unwrap them. And here's what gives me hope about this discovery. 20 years ago, we had no confirmed interstellar objects. The idea that material from other star systems might pass through our solar system was theoretical. We had no data, no observations, just models and speculation. Today, we've detected 3 interstellar visitors. We've measured the mass of one at 33 billion tons with remarkable precision. We've analyzed its chemical composition, studied its structure, and developed competing theories about its origin. That's extraordinary progress in less than a decade. And it's accelerating. New survey telescopes coming online will survey the sky faster and deeper than any instruments before them. Astronomers estimate they might detect one interstellar object per year, compared to the handful we've found so far. 3I. Atlas isn't the end of this story. It's the beginning. Each new interstellar visitor will add another piece to the puzzle. Over time, we'll build a statistical picture of what's wandering between the stars. The mystery of the 3 billion-ton comet may take years to fully solve. But we're watching science happen in real time, and that's extraordinary. But the mass of 3I, Atlas, isn't the only mystery this interstellar visitor has delivered. In my next video, I'm diving into the bizarre chemical signatures detected in this comet's coma isotope ratios that scientists say shouldn't exist and might rewrite our understanding of how matter forms in the universe. And after that, we're exploring what happens when 3I, Atlas, reaches its closest approach to the Sun, and why some astronomers are concerned that intense solar heating might cause this 3 billion-ton giant to fragment into pieces. If you found this video valuable, subscribe to Deep Space Revealed and hit that notification bell. I release new deep dives into cosmic mysteries every week, and you won't want to miss what's coming. Thank you for spending these 16 minutes exploring the impossible weight of our interstellar visitor. In a universe filled with wonders we're only beginning to understand, the fact that a 3 billion-ton messenger from another star is passing through our cosmic neighborhood reminds us that we live in extraordinary times. We are the first generation of humans to witness and weigh material from beyond our solar system. Keep looking up, keep questioning, keep exploring. This is Deep Space Revealed, and I'll see you in the next one.